Section: Introduction. In this section, we discuss the bitter lesson, which has significantly influenced advancements in machine learning and artificial intelligence. This concept highlights that general-purpose methods that effectively utilize large amounts of computing power and data tend to outperform specialized techniques created by experts. Notable examples include transformer models designed for predicting the next token, which surpass task-specific natural language processing systems, and transformer encoders in computer vision that perform better than CNN models. We also observe this trend in the ongoing efforts to enhance large language models, LLMs, to understand and generate various types of data, like text and images, using a single model. A common approach in the literature involves modeling image tokens with discrete tokens derived from vector quantized variational autoencoders, VQVAEs. However, a limitation of these methods is that the conversion between images and tokens relies on a separate, fixed encoder and decoder that may not be tailored to the specific task, potentially hindering performance. To create a versatile architecture capable of generating multiple data types without relying on pre-trained components, we introduce a new generative model called JetFormer. This model can be trained from the ground up and optimized for the likelihood of raw training data, specifically for text and images. We achieve this by combining a normalizing flow, which provides a soft token representation of images, with a decoder-only transformer and a soft token Gaussian mixture loss. The core idea behind JetFormer is that a robust normalizing flow, which we refer to as a JET, can effectively encode images into a latent representation suitable for autoregressive modeling. Raw image patches are complex, making direct autoregression challenging, and there has yet to be a convincing demonstration of this approach. Our flow model, however, is lossless and can be trained alongside the autoregressive model in an end-to-end manner. During inference, we have an image decoder available since our flow model can be inverted easily. While we focus on optimizing for log likelihood, we recognize that this alone does not ensure the generation of images with global coherence. To address this, we guide the model to emphasize high-level information through two strategies. First, we introduce a novel technique involving image augmentation during training, where we add Gaussian noise that decreases over time. This approach encourages the model to prioritize high-level information early in training. Although inspired by diffusion models, our method differs technically and does not perform progressive image denoising during inference. Second, we explore managing redundancy in natural images. JetFormer allows us to exclude certain redundant dimensions from the autoregressive model, and we also investigate using principal component analysis, PCA, to reduce image dimensionality. We conduct experiments on generating images conditioned on ImageNet classes and on large-scale multimodal generation, demonstrating that JetFormer effectively scales for both text-to-image generation and vision language understanding. In summary, our contributions include presenting JetFormer, a generative model that combines a transformer and a normalizing flow, capable of being trained from scratch to jointly model text and raw pixels. We show that our noise curriculum-based image augmentation significantly enhances the image generation quality of likelihood-based models. Additionally, we demonstrate that our end-to-end model competes well with less flexible techniques when trained on large datasets, generating both images and text. In the related work section, we note that generating natural images autoregressively as sequences of discrete valued pixels has been widely studied using CNNs and transformers. While these models achieve high log likelihood, they are computationally intensive and struggle with high-resolution images. Normalizing flows, which are invertible models trained to map image pixels to a simpler prior, scale better but often yield lower likelihood and fail to produce high-quality images. Recently, techniques that compress high-dimensional image pixel data into lower-dimensional sequences of discrete tokens using pre-trained VQVAEs have gained traction. These compressed sequences are then modeled with transformer decoders, providing a scalable method for high-fidelity image generation. VQVAEs typically use perceptual and GON losses for semantic compression and are common in dense prediction tasks, especially for joint modeling of multiple modalities. Some studies have shown that combining an autoencoder with an autoregressive transformer can be effective for continuous valued sequences without quantization. Additionally, VQVAEs are increasingly popular in vision language models, VLMs, which are often trained from scratch on large datasets or built by combining pre-trained vision and language models. To enable pixel outputs, a straightforward method is to extend the text vocabulary with VQVAE tokens. Other research combines VLMs with latent diffusion models to facilitate image generation. JetFormer relates to this category but does not depend on any pre-trained VQVAE vision encoder or decoder. Section Summary. In this section, we introduce JetFormer, a novel generative model that combines a transformer and a normalizing flow, allowing for end-to-end training on both text and raw pixel data without relying on pre-trained components. We demonstrate that our approach, which incorporates a noise curriculum for image augmentation, significantly enhances image generation quality and scales effectively for multimodal tasks. Section Method. In this section, we discuss the challenges of modeling natural images using autoregressive transformers. While modeling in pixel space is possible, it quickly becomes too demanding in terms of computation. For instance, an image size 256 by 256 with 3 color channels would require us to predict nearly 200,000 tokens. To address this, we can model images at the patch level, but this introduces its own difficulties, as each patch represents a complex distribution and capturing pixel interactions in one go is problematic. Currently, a common solution is to use a separate image encoder and decoder that converts images into a sequence of tokens, which helps reduce computational load through semantic compression. However, this method has drawbacks, such as potential loss of precision due to compression and reliance on a pre-trained encoder that may not fit our specific modeling needs. To tackle these issues, we introduce JetFormer, a generative autoregressive model that can handle both text and images while learning directly from raw data. Our model is trained end-to-end, avoiding any lossy encoders. We base our approach on 2 main ideas. First, we utilize continuous tokens, or soft tokens, to represent images. This allows us to generate high-quality images by using a Gaussian mixture model to model the likelihood of these soft tokens. Second, instead of a pre-trained variational autoencoder, we employ a normalizing flow model to create a soft token representation that is suitable for autoregressive modeling. Since flow models are lossless, they prevent representation collapse and can be trained alongside the transformer model, enabling complete end-to-end learning from raw images. We also combine these insights with standard transformers for text, creating a unified multimodal model that learns from both image and text data. Specifically, we model an image using a normalizing flow that maps it into a sequence of soft tokens while preserving the input dimensions. These embeddings are then processed by a deep autoregressive model, where we maximize the log likelihood of the image. To ensure accuracy, we add uniform noise to the input images, which helps us optimize a lower bound on the discrete image log likelihood. Both the autoregressive model and the flow model have learnable parameters that we optimize using gradient-based methods. Essentially, JetFormer operates as an autoregressive model where the inputs and targets are generated by the flow model, which re-encodes the input images. While JetFormer performs well initially, we have identified several enhancements that significantly improve image quality. These include factoring out redundant dimensions, using classifier-free guidance during sampling, and implementing a novel noise curriculum. By recognizing that natural images are often redundant and low-dimensional, we can improve model quality and reduce computational demands. We can model some dimensions with a Gaussian distribution while allowing the autoregressive model to handle the rest. This approach helps us efficiently process the output dimensions of the flow model. Additionally, we reshape the input images into flattened patches and apply a learnable linear transformation to separate important dimensions from redundant ones. This transformation allows us to model the significant channels with the normalizing flow while treating the remaining channels with a Gaussian distribution. Our findings suggest that this method is akin to applying probabilistic PCA, and we observe that initializing our transformation with PCA yields similar results. Section Summary. In this section, we address the challenges of modeling natural images with autoregressive transformers by introducing JetFormer, a generative model that uses continuous soft tokens and normalizing flows for lossless image representation, allowing for end-to-end training without reliance on lossy encoders. We also enhance image quality by factoring out redundant dimensions and employing classifier-free guidance, which optimizes the model's efficiency and performance. Section: Classifier-free guidance. In this section, we discuss classifier-free guidance, CFG, a technique commonly used in diffusion and autoregressive image modeling that enhances sample quality. We utilize a distribution-based variant through rejection sampling for Gaussian mixture models, GMMs, without any changes. Next, we introduce a noise curriculum during training. To enhance image quality, we often break down data into meaningful components. One method involves treating RGB pixels as sequences that increase in color depth and resolution. Adding noise to RGB pixels is akin to lowering color depth and resolution. This perspective leads us to view diffusion models as learning hierarchical representations in pixel space based on a noise schedule. We modify our training by implementing a noise curriculum, where we add Gaussian noise to pixels during JetFormer training. Initially, we apply strong noise, which decreases over time according to a cosine decay schedule. At the start, with high variance noise, JetFormer focuses on coarse image details. As training continues, the model refines its understanding of finer details while retaining previously learned patterns. By the end of training, JetFormer uses the correct distribution for training. This approach emphasizes high-level image structure without compromising performance. Importantly, in our method, the noise curriculum serves as data augmentation during training, and the model does not rely on noise magnitude during inference. Instead, it generates images autoregressively in the latent space of a normalizing flow. We also explore JetFormer for multimodal generative modeling, enabling the model to handle both discriminative and generative tasks for images and text. We train on sequences of image-text pairs from the web, without a post-training step, allowing us to investigate tasks like captioning and visual question answering, as well as text-to-image generation. We extend our image generation method to this setup by incorporating a transformer backbone that generates soft tokens and models language tokens with a separate prediction head. We train on sequences of image tokens followed by text tokens and vice versa, applying loss only to the second part of the sequence. We found that applying loss to the entire sequence yielded poorer results, likely because predicting an image prefix is challenging. We anticipate better results with interleaved sequences, which may provide stronger conditioning. For text-to-image generation, the text prefix conditions the model, while for image-to-text generation, the normalizing flow acts as an image encoder. The model uses the same soft token space for both tasks. In our experiments, we adopt a simple transformer-based design for the normalizing flow model, utilizing affine coupling layers that predict scale and shift. We employ channel-wise splitting, as spatial splitting did not enhance modeling quality in our preliminary tests. Our model consists of 32 coupling blocks, each with 4 or 6 VIT blocks of width 512 and 8 attention heads. The input and output feature shapes vary based on whether we feed the full image or use dimensionality reduction techniques. For image sizes of 256 by 256 and patch sizes of 16, we achieve specific dimensions after flattening and reducing dimensionality. For the latent autoregressive decoder-only backbone, we use the GEMMA architecture, considering 3 model sizes with 350 million, 750 million, and 1.3 billion parameters, inspired by previous models for image generation. For the GMM prediction head, we typically set the number of mixtures to 1024, using multivariate Gaussians with diagonal covariance. For text, we utilize a sentence piece tokenizer with a vocabulary size of 32,000, trained on the English portion of the C4 corpus. We limit the maximum number of text tokens to 64 and do not explicitly model padding tokens during training. When training for class conditional image generation, we use 16 learned tokens per class to enhance sample quality. Section Summary. In this section, we implement classifier-free guidance to enhance sample quality and introduce a noise curriculum during JetFormer training, where we progressively reduce noise to help the model learn image details effectively. We also explore multimodal generative modeling with JetFormer, allowing it to handle both images and text, and describe our architecture, which utilizes a transformer-based design for efficient image and text generation. Section: Training Recipe. In this section, we describe our training approach. We train the latent decoder-only backbone using sequences that combine discrete text and soft tokens, applying teacher forcing for negative log likelihood, NLL, based on the token distributions. We randomly choose whether each sequence is image text or text image for each example. We train the normalizing flow, which acts as a learnable patch embedding, alongside the transformer backbone in an end-to-end manner. This process is straightforward because the NLL for the Gaussian mixture model, GMM, is differentiable with respect to both the GMM parameters and the soft tokens. When we train for captioning with an image prefix, we stop the gradient at the flow output during pre-training, as we found that passing the gradients did not enhance performance. We utilize the Atom optimizer with a learning rate of 0.001, a weight decay of 0.0001, a beta parameter of 0.95, and we normalize the gradients to 1.0. Our batch size is set to 4,000, and we apply a dropout rate of 10% at the output of the self-attention and MLP blocks, which improves the quality of the generated images. For both class conditional and text-to-image generation, we randomly drop the conditioning 10% of the time and replace it with a learned token. We apply an RGB noise schedule to the input images, starting with a noise standard deviation of 64 and decaying it to 0 for the ImageNet setup and to 3 for the multimodal setup. Inspired by the VAE-based GIVT, we add Gaussian noise with a standard deviation of 0.3 to the flow latence. We normalize the image NLL to bits per dimension and apply a weight of 0.0025 to the text NLL to ensure that the loss magnitude is similar for both modalities. For our training data, we use ImageNet 1K for class conditional image generation and image text pairs from the WebLI dataset for multimodal generation. We resize images to have a shorter side of 256 pixels while maintaining the aspect ratio and extract a central crop of 256 by 256 pixels. Besides the previously mentioned RGB noise, we only apply random left-right flipping as augmentation for ImageNet 1K. We train for 100 epochs for ablations and 500 epochs otherwise on ImageNet 1K, while on WebLI, we train with 1 billion examples per modality. For evaluations, we follow the diffusion literature and use the Admiral FID evaluation suite with 50,000 reference samples, along with precision and recall metrics to assess image quality on ImageNet 1K. For text-to-image tasks, we use the MS COCO FID 30K, generating images for captions from 30,000 randomly sampled COCO validation images and evaluating against the full COCO validation set. We report metrics both in a zero-shot setting and after fine-tuning on the COCO training set. For image understanding tasks, we consider zero-shot classification on ImageNet and fine-tune for image captioning and visual question answering, reporting relevant scores. In terms of class conditional image generation, we present the sample quality of our JetFormer model trained on ImageNet at a resolution of 256 by 256 pixels, comparing it with various baselines. Despite being a straightforward NLL model without advanced image encoders, our JetFormer shows competitive performance. Notably, it achieves a high recall of 0.56, which we believe is due to its explicit log likelihood modeling, helping to avoid mode collapse. We also observe that modeling images after PCA transformation yields slightly worse results, indicating that while PCA reduces the importance of the noise curriculum, focusing on high-level image information is crucial for visual quality. This suggests that manual preprocessing can lessen the need for complex modeling techniques, yet effective end-to-end modeling remains superior when executed properly. Section Summary. In this section, we describe our training approach for a latent decoder-only model, utilizing teacher forcing for negative log likelihood, NLL, on concatenated text and soft token sequences, while training a normalizing flow alongside the transformer backbone. We detail our training data, evaluation metrics, and the performance of our JetFormer model on class conditional image generation, highlighting its competitive quality and high recall despite being a simpler NLL model. Section: Effect of the Noise Curriculum. In this section, we explore the impact of varying levels of initial noise. We found that for images size 256 by 256, starting with noise that has a standard deviation of 64 and reducing it to 0 during training yields the best results for the ImageNet setup. Specifically, initial noise levels of 128, 64, 32, and 0 resulted in FID scores of 8.62, 7.84, 8.59, and 44.71, respectively. In the multimodal setup, we noticed that reducing the noise standard deviation to 3, while keeping a small amount of noise, enhances the FID score. We provide further analysis of the relationship between negative log likelihood, NLL, and FID in the appendix. We illustrate the effects of the noise curriculum with an initial standard deviation of 64. We see that, compared to a model without noise, the final NLL does not change significantly. However, during the early training stages, the NLL is much worse due to the high noise levels. Additionally, we observe a significant improvement in FID when the noise curriculum is applied, which is also reflected in the final samples from both the noise-free model and the noisy model, with the latter showing a clearer high-level image structure. Next, we present our multimodal JetFormer models of various sizes, trained for text-to-image generation, T2I, and both T2I and image-to-text generation, TNI. We include zero-shot samples in the appendix. In both scenarios, increasing the model size enhances quality. However, training for mixed TNI generation slightly reduces T2I quality but also improves the model's vision language understanding. We compare our T2I and TNI JetFormer models with existing models from the literature. Previous work that trained generative models on image-text pairs using pretrained VQVAE achieved better T2I performance but fell short in understanding capabilities. This highlights the advantages of using unquantized, end-to-end learned features for understanding tasks. Our JetFormer models also come close to the understanding performance of image-text models like CLIP and Kappa, despite being significantly smaller. Lastly, we present a TNI baseline using a pre-trained, frozen VAE instead of an end-to-end trained normalizing flow in the appendix, and we find that JetFormer clearly outperforms this baseline in T2I generation and all image-to-text tasks.